planet is capable of unleashing extreme chaos. Volcanoes, earthquakes, hurricanes, and floods can cause untold devastation. We may think we've seen the worst Mother Nature can throw at us, but scientists struggling to understand these disasters are discovering evidence that even more extreme events have struck in the past.
This is one of the largest eruptions in the last 10,000 years.
They're uncovering clues that the worst catastrophes in history could strike again. Of all the forces of nature, volcanoes are among the most devastating. They have the power to kill millions and disrupt the fabric of modern life.
Volcanoes are some of the most dangerous natural phenomena on Earth. They can have a global impact.
Today, there are more than 1,500 active volcanoes on Earth. About 50 erupt every year. Many are well known, like Vesuvius in Italy and Mount St. Helens in the United States. But could there be other slumbering giants that we have never heard of? Volcanoes that were once even more powerful and destructive than today's monsters. That's what a series of clues is suggesting. Scientists working across the world are unearthing evidence of a cataclysmic event, a mysterious eruption that could have been one of the largest in human history. And the trail of clues starts in a very unexpected place. Here, in the heart of London, in the 1990s, archaeologists uncovered a surprise. While excavating the medieval Spitalfields Cemetery, they happened upon a series of mass graves on the edges of the burial ground. Over 4,000 men, women, and children packed into large pits. The cause of death was not obvious. So what killed so many people? And why were they all buried together?
When we find mass burial pits, we know that there's been a lot of people dying very quickly and something has gone very wrong.
As a first step to identifying the killer, archaeologist Don Walker and his team conducted radiocarbon tests to find out how long ago they died. The hope was that they could tie their deaths to some historical event. But what they found merely deepened the mystery. The victims all died around 1250 AD. That ruled out one of the most notorious mass killers of the past, the Black Death, which ravaged Europe about a century later in 1348. So what could have caused this tragedy? Don Walker needed further evidence. So he consulted ancient historical records from the period. This manuscript is a history of England, over 750 years old. It was written in Latin by a monk named Matthew Paris. Among these chronicles, one account stands out. A description of bitterly cold weather around London in the spring and early summer of 1258 that killed crops and livestock and led to a deadly famine.
It says, owing to the scarcity of wheat, a large number of poor people died, and dead bodies were found in all directions, swollen and livid.
Then Walker discovered a description that seemed to match the discovery of the mass graves.
when several corpses were found, large and spacious holes were dug in the cemeteries, and a great many bodies were laid in them together. And of course, as soon as I saw that, I got very excited because it's exactly the kind of thing that we found at St Mary's Spital, where they were digging these huge pits.
According to this text, the famine killed over 15,000 people in London, 30% of the city's population at the time.
You're talking about something that was perhaps nearly as deadly as the Black Death.
It was possibly as widespread too. Other sources reveal the far-reaching impact of the extreme weather and its disastrous effect on crops.
There are various records from this period, 1258, 1259, 1260, in various parts of Europe and as far as Japan, that do attest to extreme impacts in terms of famine in particular.
Something devastating had plunged much of the Northern Hemisphere into a pattern of bitter winters and summers blighted by torrential rain.
We thought perhaps this was something to do with some catastrophic event.
Only one type of natural disaster could have such a widespread impact on the climate. A massive volcanic eruption. But which volcano was the culprit? Walker became intrigued by one of the most massive eruptions in recorded history, one that had impacted much of the Northern Hemisphere, even though it was located half a world away. Mount Tambora in Indonesia. In April 1815, eyewitness accounts record that Mount Tambora erupted explosively.
And this is one of the largest eruptions of the last 10,000 years.
It's estimated over 60,000 people died in the shadow of this volcano. But the eruption had an even more far-reaching impact. In Northern Europe and North America, the year after the eruption, 1816, is known as the Year Without a Summer. In New York, it snowed in June. In Europe, cold weather led to the worst famine for a century.
The climate change caused agricultural failures, poor harvests, it pushed up grain prices, with many people perishing from malnourishment.
So perhaps another powerful eruption could have caused the Year Without a Summer in 1258.
We began to think that perhaps this might be something to do with what had happened back in the 13th century. Perhaps this was why the people starved.
But to pinpoint the location of the mysterious volcano, they needed to know more about the type of eruption. They looked at one of the largest volcanic events in recent memory. The 1991 eruption of Mount Pinatubo in the Philippines. Pinatubo killed 847 people locally and left over 200,000 homeless. But, as with Mount Tambora, this eruption also had far-reaching effects. NASA satellites were able to monitor the eruption. Pinatubo blasted out 5 cubic kilometers of superheated ash. But it also ejected hundreds of millions of tons of volcanic gases in a plume 35 kilometers high.
The ash and the gases are dispersed through the atmosphere by the wind, and they can travel thousands of kilometers, tens of thousands of kilometers.
But unlike heavy ash that soon falls out of the atmosphere, the lightweight gases persist for much longer.
The most impactful gases are the sulfur-rich gases, and those gases will form little droplets of sulfuric acid in a large cloud.
The tiny drops of sulfuric acid are called aerosols. And in a large cloud high in the upper atmosphere, these aerosols caused enough sunlight to reflect back into space to cool the planet. the satellite data revealed that this sulfuric acid mist had a much more dramatic impact than the ash. It blocked enough sunlight to cool the entire planet by 0.5 degrees Celsius for 2 years.
That doesn't sound very much, but it actually masks much stronger regional variations. And that translates into real impacts on the ground in terms of crop yields.
In 1258, the temperature drop was much greater than that caused by Pinatubo. This suggests that whatever triggered this medieval disaster could have been much bigger.
That indicated that a big event occurred somewhere in the world, but there was no record of massive volcanic eruption.
For volcanologists, it was the biggest mystery for us.
So where was the culprit volcano? And after more than 750 years, how could anyone identify the killer? About 1,400 kilometers from the North Pole, researchers for the Greenland Ice Sheet Project are taking core samples from deep in the ice. Ice that could hold evidence of a vast volcanic eruption. The ice sheet here was built layer by layer as snowfall accumulated over 130,000 years. The deeper into the ice the scientists drill, the further back in time they can look. At the Desert Research Institute in Nevada, glaciologists Nelia Dunbar and Joe McConnell are preparing to analyze an Arctic ice core sample that contains snowfall from the mid-13th century. The core comes from more than 300 meters below the surface of the ice sheet. They'll be looking for sulfuric acid, evidence of an intense eruption.
If there were a big volcanic eruption and it produced a lot of sulfur, that sulfur should be preserved in this ice. And that's what we're interested in studying. Where is this from? What's the age of it?
So this piece is from around 1250, 1255 AD. This represents about 3 years. So this is roughly 1 year, roughly 1 year, and roughly 1 year.
These ice cores hold an incredible record of past climate. In between the snow crystals are little pockets of atmosphere that are little time capsules that represent the composition of the atmosphere at the time the snow fell. Over time, more snow will fall on the ice sheet, and that record is locked in.
Up to the right, and then up to the left.
But to unlock the record, scientists have to carefully melt the ice.
Okay, so now we're ready to start the analysis.
As each layer of ice melts down, the meltwater passes through a mass spectrometer. This is able to read out the chemicals that were in the atmosphere hundreds of years ago. As the results start to come through, the team immediately sees a telltale spike.
So we're seeing the responses come up on all the various instruments right now. So this would be 1258, and you can see the acid now has just skyrocketed, a huge increase in sulfur. So it's certainly pointing to volcanism.
Okay, so that must have been a really big volcanic event.
Yeah, absolutely huge.
The sulfur locked inside the 1258 ice layer tells the story of a powerful volcanic eruption. And though the sulfur precipitated out of the atmosphere in rain and snow in 1258, the eruption itself likely occurred the year before.
Now, keep in mind that it takes a while for the sulfur to make it from the volcano through the atmosphere and be deposited on the ice sheet. And so this event probably occurred in maybe mid to late 1257.
And the amount of sulfur ejected by this eruption was vast by comparison with other eruptions also captured in the ice cores.
Here's the 1257 event that we just measured again in this new ice core. We can see that it's huge when you compare it to Tambora Here in 1815, it's you know, something like more than twice as big. So this is a really, really big event. And at least in this composite, it's the biggest event of the last 2,000 years, very clearly.
So this eruption seems to have been large enough to account for the freak climate disaster across the Northern Hemisphere in 1258, including London's deadly famine.
It's hard to really pin down one event and say this was the result of a volcanic eruption. But I think in this case, the evidence is quite strong.
You can imagine living in medieval London. You know that you haven't got enough food to live, your crops are failing, the weather's very bad, but you'd have no idea the true cause of what was going on.
The true cause was that somewhere on the planet, in 1257, a volcano exploded and blasted its contents, including poisonous gas and ash, high into the atmosphere, where it dimmed the sun for months, if not years. But where was this killer?
The mystery that remains is what was the volcano that was responsible for this big volcanic eruption?
More than 1,500 volcanoes have been active in the last 10,000 years. So pinpointing which of these caused such a massive disruption in 1258 is a huge challenge. How could scientists work out which volcano was the culprit? In her lab at the New Mexico Bureau of Geology, Nelia Dunbar examines some distinctively shaped mineral particles lodged in a section of ice from a different Greenland ice core. The particles also date to 1258, when the sulfur concentrations were highest. Could these particles be clues to the volcano's identity? At 50,000 times magnification, it's clear that the mineral particles are actually microscopic pieces of volcanic ash.
These particles are smaller than a human hair.
The ash particles are fragments of shattered pumice, produced when magma cools rapidly during an eruption. And their chemical composition is unique to each volcanic eruption.
Just like a human fingerprint allows a suspect to be identified, the chemical composition of an ash layer allows the source volcano to be identified.
This unique signature didn't match any known volcano. But it did show up in one other surprising place. At the exact opposite end of the world. In ice cores taken from the South Pole. These cores also contained a significant spike in sulfuric acid, corresponding to the eruption in 1257. It was evidence of one single giant eruption that had covered both hemispheres, with a cloud of sulfuric acid. Climatologist Michael Mills believes the size of this global cloud can help pinpoint the place where the volcano erupted. He uses satellite data to map how clouds of sulfuric acid aerosols disperse around the world.
Let's look at what happens when you have an eruption in the Northern Hemisphere. In 2008, we had several eruptions, and the aerosol stays in the Northern Hemisphere. Now look at what happens when you have an eruption in the Southern Hemisphere. The aerosol spreads and will remain in the Southern Hemisphere.
But how could an aerosol cloud reach both hemispheres? For that, an eruption has to occur within a narrow band around the middle of the globe.
This is Pinatubo in June of 1991 in the Philippines. It starts spreading throughout the tropics, and from there it spreads into the Northern Hemisphere and to the Southern Hemisphere. Within a year after the eruption, the aerosol has covered the globe from pole to pole with affecting temperatures globally.
The mystery eruption of 1257 also spread a cloud of sulfuric acid over both poles. So it too must have erupted near the equator. But that still leaves over 700 possible volcanoes as suspects. But which one? And could it strike again?
It's still a needle in a haystack to find the one volcano, the one eruption that triggered all of this. Because there are so many volcanoes, even if you narrow it down to the tropics. Where do you start?
It seemed an impossible mystery to solve. But then, a French geographer named Franck Levine decided to take it on.
For me, it looks a bit strange that nobody found this eruption. So I decided to take up the challenge.
He approaches it as a detective.
Trying to find the identity of this mystery volcano was like a crime scene. So we needed to investigate, to look for culprits, to look for clues.
Volcanologist Jean-Christophe Komarovsky joins the investigation.
It's a very large eruption. It's an unknown eruption, so it has to be in a country where there are many, many volcanoes. Most of them perhaps have not been studied.
The team start by looking at the region known as the Pacific Ring of Fire, home to 3/4 of the world's active volcanoes. These volcanoes mark the boundaries of the giant plates of rock called tectonic plates. And near the equator, where 2 of these giant plates collide, is Indonesia, the most active part of the Ring of Fire. A country with 129 active volcanoes spread over 5,000 kilometers.
Indonesia has the second largest number of active volcanoes in the world.
Here, one plate dives under the other in a process called subduction. The rock on the underside of the upper plate melts, forming giant bubbles of magma that rise up, forcing their way through the Earth's crust until the magma erupts at the surface. So which of Indonesia's volcanoes could have exploded so catastrophically in 1257? In his hunt for a giant eruption, geographer Franck Levine searches for large craters and other telltale clues.
And one of these clues is a large volume of pumice all around the volcano.
Pumice, a rough textured rock, is solidified magma, blasted out during explosive eruptions. It can be a deadly material. When Mount Vesuvius erupted in Italy in 79 AD, it entombed the town and the people of Pompeii in layers of pumice nearly 5 meters deep. Throughout Indonesia today, pumice mines dig out this volcanic material, primarily for use in the construction industry. And the scars left by the quarrying work are so extensive, they're visible from space. Journeying to Indonesia, Levine works with partners from the government's geological agency and Universitas Gadjah Mada. They visit several volcanoes with no success. At each site, the pumice is compacted and hard, likely too ancient to have been created during the 1257 eruption.
Yang juga kelihatannya lebih tua daripada yang diperkirakan. Jadi lebih tua dari abad ke-13.
Then the team sees something intriguing in the satellite images and decides to narrow its search to the island of Lombok, just east of Bali.
This island is quite a big island with a very big crater.
Stretching 6 kilometers across and 800 meters deep, this giant crater is called a caldera. It's what remains of a volcanic system known as Mount Rinjani.
When you have a very large explosive eruption, you're left at the end of the eruption with a huge hole.
To the team's expert eyes, it looks like there were not one, but two giant volcanic peaks here in the past. Mount Rinjani itself, and a second peak that once rose above the main part of the caldera. Today, inside this caldera is now a small volcanic cone, Mount Barujari. Surrounded by a rainwater lake, Mount Barujari is the part of the volcanic system that is still active. In 2015 and 2016, this small cone erupted with enough force to send plumes of ash thousands of meters into the atmosphere, disrupting international flights in the area. It's far too small to be the source of the mystery eruption. But the caldera it sits in is large enough to have been created during a much more powerful eruption. And there's evidence of this potential eruption all around the volcanic system.
Everywhere in the island you can find a pumice quarry.
It may be possible to date the pumice deposits in these quarries. So the team travels to Lombok. And the hunt starts in the shadow of Mount Rinjani. A peak that soars nearly 4,000 meters high. The team joins forces with experts from the Indonesian Institute of Sciences and Mataram University. They head for the quarries identified in the satellite images. And as soon as they arrive, they discover something remarkable. The volcanic pumice deposits are at least 40 meters deep.
Here we are looking at a huge volcanic deposit, and that's very rare to find so thick deposit very far away from the summit of the volcano.
Pompeii, just over 9 kilometers from the erupting Mount Vesuvius, was buried under almost 5 meters of pumice. Here, the deposits of pumice and ash are nearly 8 times thicker. And they are much further away from Mount Rinjani than Pompeii was from Vesuvius. It's a sign of a giant eruption.
You're dealing with a very massive eruption, much larger than the Pompeii eruption, and probably also much larger than the Pinatubo eruption in 1991.
And it looks to them as though the ash and pumice flowed down from the volcano in vast avalanches.
You can see it's very rich in finer material. It's not pumice falling from a column, raining down. It's an avalanche of incandescent hot volcanic rocks mixed with gases.
My first impression when I saw such huge deposit was that we have here a very serious candidate for the mystery eruption.
But is all this pumice from the mystery eruption of 1257?
To confirm that this eruption is the 1257 eruption, we need to try to find charcoal, wood logs that were burned by this eruption, carried by the pyroclastic flow and settling here, and we need to date those.
If they can find burned wood, they can radiocarbon date it, since unlike pumice, wood contains carbon absorbed from the atmosphere. And by taking samples of the pumice itself, the team hopes to compare its chemistry with the fragments of volcanic ash from the polar ice cores. But Levine still needs more evidence. so he decides to investigate Lombok's past to see if he can find records of historic eruptions. Under lock and key in the museum of Lombok's capital city, Mataram, is an original text, written on dried palm leaves in an old Javanese script. Called the Babad Lombok, this text is a rare account of Lombok's history.
Yang menceritakan tentang sejarah Lombok dari zaman prasejarah sampai zaman sejarah.
And hidden in this document is a remarkable account that historians have dated to the 13th century.
Gunung Serenjani longsor dan Gunung Samalas runtuh. Banjir batu gemuruh.
It describes a huge volcanic eruption that occurred in Lombok.
Levine is familiar with Mount Rinjani, mentioned in the text, but not the name of the volcano that's described as collapsing, Mount Samalas.
This description is absolutely fantastic because it mentions the name of a new volcano, Mount Samalas. I never heard about this before.
This remarkable discovery raises a new question. Could the giant caldera the team saw on satellite images belong to the unknown Mount Samalas? The text is a tantalizing clue, but could it just be a myth?
It made this volcano our chief suspect in our investigations. But to confirm it was the one, we needed scientific proof.
So the team decides to mount an expedition to trek into the mountains and hunt for hard evidence at an altitude of over 2,500 meters. From up here, the team can assess the landscape and geology in a way that is impossible from satellite images alone. Exposed in the cliffs are geological layers that allow Jean-Christophe Komarovsky to work out the sequence of events that led to what can be seen today. The giant caldera.
These cliffs here mark the remains of a very massive volcano.
And towering over the east side, the remains of Mount Rinjani.
You can see the slopes of Mount Rinjani volcano rising to 3,700 meters. And it was much higher before.
The scars in the cliffs suggest to Komarovsky that half of Mount Rinjani avalanched into the caldera after it formed.
The formation of the Samalas caldera destabilized Mount Rinjani, which collapsed into the caldera, and this formed this massive sheer cliff here.
To the experts, it looks like Mount Samalas once stood next to Mount Rinjani, just as the ancient text describes.
Ternyata hasil penelitian terbaru bahwa ada tubuh gunung api yang bernama Samalas yang akhirnya memang ternyata berbeda dengan gunung api Rinjani.
By extending the existing slopes of the volcano, experts have reconstructed what Mount Samalas looked like.
Imagine that before an eruption, you had a huge conical volcano rising 1.6 kilometers above the rim of this giant hole.
So how did several cubic kilometers of rock disappear and leave an enormous caldera in its place? It had to begin with a giant eruption.
And in order to form a caldera, you have to have first a very massive explosive eruption.
In a magma chamber far beneath the volcano, the pressure rose and finally cracked open the rock above. Magma blasted upwards. As this chamber emptied, it became unstable.
This destabilizes the whole volcano on top.
The roof of the partially empty chamber then cracked under the weight.
And it collapses.
The entire top of the volcano caved in. Billions of tons of rock disappeared as it fell hundreds of meters down into the magma chamber below, forming a giant crater above. The enormous caldera. But that wasn't the end.
As the volcano collapses on itself, it forms a massive explosive eruption, producing giant pyroclastic flows that sweep down the flanks of the volcano.
This catastrophic event explains the depth of the pumice deposits in the quarries and closely aligns with the ancient story in the Babad Lombok.
It gives a name to the volcano that existed at the beginning of the eruption, Mount Samalas. And it describes how Mount Samalas collapsed and on itself. Altogether, the description in the Babad matches remarkably what we have found in our field investigations.
We now know that the Babad was not a legend, but eyewitness accounts.
If the long-forgotten Mount Samalas was the source of the giant eruption on Lombok, as the evidence suggests, could it also be the mystery eruption of 1257? To find out if Mount Samalas caused a global volcanic winter in the Middle Ages, the team need forensic evidence. First, to accurately assess just how big the eruption was, they take samples of pumice and ash from over 100 different sites across Lombok and on neighboring islands. In this case, pumice fragments 5 centimeters across were found 46 kilometers away on the nearby island of Sumbawa, allowing the team to calculate that the pumice likely ascended nearly 43 kilometers high. More than 15 kilometers higher than the Mount St. Helens eruption of 1980.
This is one of the highest column heights for explosive eruptions in the last 10,000 years.
The Mount Samalas eruption was certainly massive enough to cool the entire world. But can scientific tests prove that the pumice was from the mystery 1257 eruption? In Paris, French volcanologist Céline Vidal goes through the samples taken from Indonesia. First, she selects pieces of carbonized wood found inside the pumice deposits for radiocarbon dating.
On a analysé une vingtaine de morceaux de bois calciné qui proviennent de sites tout autour du volcan. Et les datations au carbone 14 nous ont montré que l'éruption date de la deuxième moitié du XIIIe siècle.
All the results were consistent with the mystery eruption.
The dates are in range, but there's one final test. Will the chemical fingerprint of this eruption match the fingerprint in the polar ice cores? At high magnification, Vidal compares the volcanic ash fragments, one from the Antarctic ice core from 1257 and one from the pumice deposits on Lombok. They appear very similar. The final test is to compare their chemical fingerprints.
J'affiche le diagramme de composition chimique de la cendre du Samalas, ici en bleu, et on voit que les pics correspondent parfaitement. Elles sont comparables à plus de 99%, et c'est vraiment excellent. Et ça permet de conclure qu'elles ont la même origine.
All the evidence reveals that the previously unknown Mount Samalas is the killer volcano.
The team was very excited by the result.
The source of the 1257 eruption has been a mystery for 30 years. So we were quite excited when we were able to prove that Mount Samalas erupted in 1257.
The mystery of the massive spike of sulfuric acid in the polar ice cores, the global volcanic winter caused by a cloud of aerosols that blocked the sun, and likely the thousands of people killed in London in a catastrophic famine, all are answered. By combining these discoveries with the investigation on the volcano, the team can now unpack the eruption blow by blow.
The 1257 eruption started with a very explosive, violent eruption from Mount Samalas.
At its peak, the eruption blasted out 1 million tons of material a second.
And that produced a very tall eruption column of ash and gases and pumice rising 43 kilometers in elevation.
About 15 cubic kilometers of pumice and ash rose 4 times higher than the operational altitude of a passenger jet. While the gases remained aloft, most of the pumice and ash then fell back to Earth.
And it produced a rain of pumice over a very vast area.
It covered an area over 700 kilometers across. During the final collapse of the volcano, 25 cubic kilometers of pumice and ash then formed giant pyroclastic flows. Racing down, they reached speeds of over 200 kilometers an hour at temperatures exceeding 800 degrees Celsius.
They covered the entire landscape of Lombok with thicknesses of 5 to 50 meters, reaching the sea in many places.
But even as the dust settled on Lombok, the vast volcanic cloud started to envelop the entire world. Even as far away from the eruption as North America and Europe.
The fact that we have so many thousands of people buried in these mass pits as a result of this volcanic eruption just shows us what a global event it was.
This was possibly the most massive volcanic eruption in recorded history. And it raises a troubling question. Could another eruption of this magnitude happen again? It's been 750 years since the giant eruption of Mount Samalas. Yet inside its vast caldera, eruptions from Mount Barujari reveal that the volcanic system is still active. 800 meters below the caldera rim, Jean-Christophe Komarovsky rejoins the team of Indonesian volcanologists, monitoring the active heart of the Samalas Rinjani volcanic complex. Using thermal imagery and making risky treks to collect lava from the latest eruptions, the Indonesian volcanologists are gaining an ever more accurate picture of the volcano's activity level today. And the most telling clue to the volcano's activity is not the cone itself, but the rainwater lake that surrounds it. Volcanologist Devi Kamal Shayabana measures the water temperature. At an altitude of 2,000 meters, this lake should have a temperature of 15 degrees Celsius.
But here we have like 20 to 22 degrees Celsius, which is much hotter than a normal lake, which indicates a very strong magmatic activity beneath the caldera.
The eruption of 1257 likely left a lot of magma behind, inside this chamber.
The volcano is still under pressure, and it is still unstable.
The volcano remains active, but their analysis tells them that there is insufficient pressure to power a 1257 scale eruption. But what about other volcanoes? According to the ice core record, there have been at least 7 explosive eruptions on the scale of Pinatubo near the equator since 1257. It will happen again. The worry is, no one knows when.
If another major explosive eruption were to happen today in the equatorial region, it would have devastating consequences.
There'll be huge disruption to global aviation.
The economic impact would be really catastrophic.
These massive volcanic events really impact on people globally, affects their climate, food source, causes famine, and can cause catastrophic numbers of deaths.
750 years ago, an eruption on a small island in Indonesia destroyed lives on the other side of the world, reminding us again of the power of our volatile Earth.